Imagine it's 2008. The test stand rumbles, and India's indigenous Kaveri jet engine throttles up, hitting its target of 81 kilonewtons perfectly on schedule. That engine immediately slides into the airframe of the homegrown Tejas fighter jet. This map shows how exclusive this is. Only the US, Russia, France, and the UK can build a combat jet entirely from scratch. Here, India becomes number 5. Owning the source code means they can push performance limits without needing a foreign veto. If New Delhi wants to sell the Tejas to a foreign buyer, they do it instantly. There is no waiting around for export licenses from Washington or Moscow. Because of this early success, the supply chain for these engines is already mature today. That gives India's current 5th-generation stealth fighter program a battle-tested propulsion system right out of the gate. But that timeline never happened. By 2008, the Kaveri prototype was severely overweight. It consistently missed its thrust targets. And worst of all, during endurance runs, the high-pressure turbine suffered repeated catastrophic failures. The government officially delinked the engine from the Tejas program that same year. To keep their new fighters flying, India had to purchase GE engines from the United States. After 30 years of research and nearly $250 million in funding, the original Kaveri program was completely sidelined. We have to look at how every other country built their military engines to understand if that investment was actually a waste. No nation builds a flawless military jet engine on their first try. The engineering tolerances are simply too tight to avoid a massive failure rate early on. Look at the American Pratt & Whitney F-100. Before it became a legendary powerhouse for the F-15 and F-16, its early development was plagued by violent compressor stalls and terrifying reliability issues. The Soviet Union went through a nearly identical process with the AL-31. It took years of deeply troubled, protracted development to sort out the complex internal mechanics during the Cold War. More recently, China spent decades pouring billions into their WS-10 program. They iterated on flawed designs for nearly 20 years before the engine finally became viable for their Air Force. This chart maps out the 4 universal stages of aerospace development: first engine, problems, iteration, and mature engine. The US, Russia, and China have pushed their hardware across the finish line. The Kaveri is currently navigating the turbulent iteration phase. The delays were the mandatory initiation fee into global engine development. Every aerospace power pays it. To understand why iteration is so difficult, you have to look at the extreme physical environment inside the casing. The turbine blades in these modern military jet engines are engineered to spin at an astonishing speed of over 10,000 revolutions per minute. While spinning at those extreme speeds, they are continuously blasted with core combustion temperatures exceeding 1700 degrees Celsius. That is physically hotter than the melting point of the metals used to build the blades. This diagram shows how engineers solve that problem. To keep the blades from liquefying, you use single crystal metallurgy. On the left, standard metal grain boundaries crack under thermal stress. On the right, a blade cast as a single continuous crystal safely survives the heat. India was attempting to master this highly advanced casting process completely from scratch. They were attempting this on a fraction of Western budgets. And following India's nuclear tests in 1998, international technology sanctions cut off their access to critical components, forcing researchers to figure it out in total isolation. The original engine didn't make it into Tejas, but pushing through that grueling isolation forced India to build indigenous testing facilities, create advanced design tools, and train a hardened generation of aerospace engineers. The DRDO never scrapped the Kaveri technology. They intelligently repurposed the core research for long-range autonomous strike drones. They created the Kaveri derivative engine. It's a dry, non-afterburning variant that produces a steady 46 to 52 kilonewtons of thrust. This engine is targeted for the Ghatak UCAV, India's futuristic stealth drone. For a flying wing drone on a deep penetration mission, the platform prioritizes mechanical reliability and high fuel efficiency over raw afterburning power. This pivot allows engineers to test and mature their core engine technology in high-altitude environments on unmanned platforms without risking the lives of human pilots. With that foundation built, India is advancing to the Kaveri 2.0 program, bringing in French aerospace giant Safran for an unprecedented full technology transfer pact. France is handing over the proprietary blueprints and casting parameters for hot section metallurgy and single crystal casting directly to Indian engineers. A technology transfer only works if the receiving country has the industrial capacity to absorb the data. India's aerospace ecosystem can only execute these designs today because they spent the last 30 years struggling through the original Kaveri program. The ultimate endgame is total self-reliance. By eliminating foreign dependencies, India secures an uninterrupted, sovereign supply chain to support its homegrown aviation fleet. Building a jet engine from scratch is arguably the hardest engineering challenge on Earth. The decades spent on Kaveri served as the mandatory, irreplaceable tuition fee for India to finally master its own sixth-generation propulsion.